I'd like to now give you an introduction to colligative properties. Colligative properties are defined as properties that are not affected by the nature of particles but simply by how many particles are present. So examples of colligative properties are freezing point depression, boiling point elevation, vapor pressure lowering and osmotic pressure. I'd like to give you examples of each of these. Freezing point depression is the situation where we put any solid on top of an ice, and it doesn't matter what the solid is. All that matters is how many particles you're putting on top of the ice. And the more particles you put on, the more the ice will melt. And what's going to happen is that the ice will melt in order to dissolve these particles that are on the surface. If the ice is melting to dissolve these, what's going to happen is we're going to have to take this down to a lower temperature to freeze it. And this is how the principle works when we put the ice on, when we put salt on ice on roads. And the idea there is to lower the melting point of the ice so that it freezes at a lower temperature, or basically turns into water at a higher temperature so that people no longer skid on the ice when they're driving. So that's the idea behind putting salt on ice. The other the boiling point elevation and vapor pressure lowering are related, and what we've got here is a liquid, and when we have a liquid we have vapor from that liquid floating around above the liquid, so that's vapor pressure, and that's going to be defined by the nature of the liquid. However, if we decide that we're going to dissolve something in the liquid, what's going to happen is vapor from above the liquid is going to come back to the liquid to help to try and dissolve what's in the liquid. So what's going to happen is the vapor pressure will end up being lowered. Now when the vapor pressure gets lowered, what's going to happen is that the boiling point will also increase. What this means is we need to have more energy put into the solution so that these vapor molecules that were pulled down into the solution end up coming back up here and boiling the solution. So you can see that these liquid and these solvent-solute interactions are what's going to cause these solvent molecules to stay within the solvent and not to go into vapor form as easily, which means we have to put more energy in. That means that we need a higher temperature to boil the liquid as well. This phenomenon is something that people are familiar with when they're cooking pasta. Often they'll add salt, and the reason for that is to increase the boiling point of the water. And that means water will boil at a higher temperature, which will enhance the cooking of the pasta. Alright, the last one is osmotic pressure, and this particular property involves putting a semi-permeable membrane on one side of a solution, and on the other side we've got a pure liquid. Now what's going to happen is that a semi-permeable membrane will allow for passage of a solvent but will not allow for passage of a solute. That's why we say it's semi-permeable. Examples of semi-permeable membranes are sausage casings and frog skin. And what you'll see here is that the water from the pure side will go through the semi-permeable membrane, and note that the solute won't be able to go back through the membrane either to even things out. So the solvent is going to come through the membrane, and if we have a piston here, the solvent coming through the membrane and trying to help dissolve the solute will add a pressure to this piston, and the piston will actually push upwards, and that pressure is called the osmotic pressure. So all of these things that we've talked about, osmotic pressure, boiling point elevation, vapor pressure lowering, and freezing point depression, are all properties that depend on the number of solute molecules that we're using, and not on the nature of those solute molecules. And those properties will end up being exemplified even more by having more and more solute molecules in the systems.